homework problem that wasn't working out. Okay, so remind me, so you had that your y was c1 e to the x plus c2 e to the minus x, right? And the g of x, meaning what it had to equal out to, was 2x, positive 2x plus 4? Like this, right? All right, so if you went using undetermined coefficients, so your particular solution, and the differential equation was y double prime minus y. Right, that, okay, equals the 2x plus 4. Okay, there we go. So your particular solution, you would have made a guess here. There's no constants or x's in your complementary solution. So your particular solution guess would have been your ax plus b. And the first derivative is a, and your second derivative is 0. And when you plug that back into the original, you're going to get 0 minus the original, which was ax plus b. And that has to match up to the right-hand side, which is the 2x plus 4. So this is just negative ax minus b equals 2x plus 4. And then you're just equating coefficients. So the numbers in front of your x's have to match, and the numbers that are constant have to match. So that tells you that negative a is 2. So a is negative 2. And negative b is 4. So b is negative 4. And so that means that your particular solution is negative 2x minus 4. Then they asked you to do the same thing using variation of parameters. So let's do that. So first thing we need is the Wronskian. Now I think I'm putting them in the opposite order of yours, Tori, so it just means we should get negative of the same thing. All right, so when I multiply along this diagonal, e to the x and e to the negative x will become 1, so that's negative 1. Minus subtracting the other direction, and that will be 1 as well. So I'm going to get negative 2. Then when we find WU, I'm replacing the first column with 0 and whatever the function was. So 2x plus 4, e to the minus x, and negative e to the minus x. The determinant there is going to be 0 minus, let's see, 2x plus 4 times e to the negative x. So that's going to give me negative, and I'm going to leave it like that and see what happens. No, you distribute yours, so we'll all do it similarly. So it's going to give me negative 2x e to the minus x minus 4e to the minus x. Then we want the WV. So we're keeping the first column and replacing the second. And that's just 2x plus 4 times e to the x. So that is 2x e to the x plus 4e to the x. Then, what number is this, by the way? Number 9, okay. All right, so to find u, then you're taking the integral of wu over w dx. So that's the integral of negative 2x e to the minus x minus 4e to the minus x all over negative 2. That's going to give us just the integral of x e to the x plus 2e integral of e, it should be minus x dx. Right? Okay. Now, this one is just going to be negative 2e to the negative x. This one, we're going to go by parts. So your u is equal to x. dv is e to the negative x. du is 1. v is negative e to the negative x. So this turns out to be negative x e to the negative x minus the negative, so that's plus the integral of e to the minus x dx. So this becomes negative x e to the minus x minus e to the minus x. And then bring the red one back, minus 2 e to the minus x. So that's going to give me negative x e to the minus x minus 3 e to the negative x. Then we want to find our v. So v is the integral of wv over w dx. So I'm taking 2x, the positives divided by negative 2. So that's going to give me integral of negative x e to the x minus 2 e to the x dx. And same kind of thing, this integral here is going to be negative 2 e to the x. And for this one, we want to go by parts. So u is equal to negative x, dv is e to the x. So du is negative 1, and v is e to the x. So this is going to give me negative x e to the x minus the negative, so plus the integral of e to the x dx. And so this gives me negative x e to the x plus e to the x. And then bring the red one back, so minus 2 e to the x. It's got to be a sign right there, Tori. You see it? Okay. And so you end up with negative x e to the x plus, nope, minus 1 e to the x. Now, when you take your u times v, your y1 times u and your y2 times v, what happens is the e part's going to cancel out. So that means you're taking your complementary solution. So y equals c1 e to the x plus c2 e to the negative x. And I am taking my u, which is this one right here, and multiplying it by e to the x. So the e parts are going to cancel. So that's going to give me negative x minus 3. And this one, I'm multiplying by e to the negative x because that's my y2. And when you do that, the e to the x's are cancel out and you'll end up with minus x minus 1. And that's where you get the same thing. Minus 2x minus 4. Okay. So the issue is there. The variation of parameters homework is the one that's due tomorrow. So, right. Let me go grab the copies. If you're going electronic toward the notes are already up there. The blank ones are the first one in the higher order models. All right, so to round out chapter 4, our goal here is to look at applications. It's kind of what we did in the first chapter, right? We went through all the strategies we had to solve, and then we looked at numerical solutions, which to do second orders, you kind of do a nested version of Runge-Kutta, but we probably won't get to that in this class. If you're taking next semester with me, we will. And I have to ask about that. Tori, I think we have 5 people now. I don't know if it'll run or not. I'm gonna go find out what adjustments they're gonna make to my schedule. But if not, we'll run it as an independent study. I don't know. I have to find out. I know they've run it before with 8, but I don't know what their minimum number is. Okay. So our biggest application of our second order equations is with mass spring systems. Okay, so we're going to kind of run through the 3 different types of mass spring systems. The first one is free undamped motion. So what you do is you take a spring, it's suspended vertically from a rigid support. So you have something, I mean, you guys, I feel like I'm, with most of you being physics, I'm like, oh, you guys think I'm nuts here. So you have something holding up a spring, and then you're going to put attach a mass to the bottom of it. Okay. This is your equilibrium position, wherever it's hanging. And then you're going to displace that from a distance so that your spring starts to move, right? So in free undamped motion, what we say is that all of this stuff is how you generate the equation. Just in there for now. Thank you, Ben. What are we doing? So free undamped motion means that there is no friction here. So you're placing this in a vacuum. So there's no air resistance. So when you pull that spring, the spring is the only thing acting on it, right? The spring and gravity. So the spring is going to pull it up while gravity is going to pull it down, and they're going to act in opposition. And you're going to get a mass that moves, right? And it's going to continue to move forever and ever and ever, and we get oscillatory behavior here. So here's how that works. If we think of this as a point mass, then the 2 things that are working on this is you've got gravity is pulling it down, right? And then the spring is pulling it up. And at equilibrium, those 2 things are balanced, right? So here's what we've got. And this is what's in here, right? So from Hooke's law, we get that the force due to the spring is K times S. Okay. So this force here is K times S. K equals mg over S, which is the spring constant, and X is the distance from equilibrium that we stretch it. Okay, so we're going to assume that at equilibrium, these 2, so this is at equilibrium. Ks is what we've got going on, right? And then this one is your gravitational force. So this is just your force. This is just your mg, right? So at equilibrium, those 2 things are balanced. So you get that Ks equals m times g. Note that S is how far the string stretches when you put the mass on it. So if you start with a spring that is that long, and when you put the mass on it, your spring now is this long, this distance here is your S. I drew that really small, so I'm going to zoom in for you. All right, so you have your spring that's coiled tightly. You're then going to put some sort of mass on it. Whatever distance that stretches, that's your S. X is then I'm going to pull that away from equilibrium and let it bounce around. So X represents the distance from that equilibrium point. Does that make sense? Okay. So what this tells me is that S is a distance that we measure based on the spring. G is regular old G, and mass is what you know. So this tells you how to find your spring constant. So that tells you that your spring constant K is mg divided by S, the weight of the mass divided by your spring constant. So that's one thing that we know. And that just comes from looking at it at equilibrium. So that's where this first part up here comes from. Okay. So now what's going to happen is we're going to pull that spring down. So if this is now, you guys love my drawings. So now I'm going to take my spring that was at equilibrium and I'm going to stretch the mass way down here. So if this is my equilibrium position, then this distance is my X. The distance that I pull it from equilibrium. Okay, so what forces are acting on it now? Well, you have the spring constant, but that's now being multiplied by the distance from the S that we took originally plus that X, right? So now your force due to the spring, so the force of the spring is going to be equal to K times X plus S. And then you have your gravitational force, which is still your mg. Right? So those are your two forces that are acting. So the total force on what's going on is going to be those two things added together. You have two forces acting. So you have K, X plus S, and mg. Okay. Now, Newton's law said that has to equal to m times your acceleration. So that's m times the second derivative of x with respect to time. And you don't have to memorize any of this. I'm just showing you where all this comes from. Now, the difference here, if we're choosing down to be positive, is that the spring is always acting opposite the mg, right? So our K is actually going to be negative. So this is equal to m d squared x dt squared, or I'm going to write it as x double prime. So m x double prime is going to be equal to negative kx plus mg minus ks. But this is just equal to 0 because of this one. Right? So ks is equal to mg. So those two cancel out. And what happens is we get m x double prime equals negative k times x. And now I want to put everything with the x terms on the left. So this is just mx double prime plus kx equals 0. And that's our equation for undamped free motion. So when you have no dampening for your spring, meaning it's sitting in a vacuum, there's no resistance against the spring whatsoever, then this is your equation of motion. When you do problems, you're going to start from here. You're going to find your mass, you're going to find your K, your spring constant, using whatever information is available, and then you're going to plug those in, and then you're going to solve a second order equation, right? M and K are constants, so this is the type with your E solutions, right? This is your constant coefficients. So you're going to use your characteristic equation and solve it, right? There's no, it's homogeneous because it's equal to 0. So all you're doing is solving using the things that we did in sections 4.2 and 4.3, right? Now, what I'm going to do here is this. If I was solving this in general, here's what I would do next. We have mx double prime plus kx equals 0. I'm going to divide everything by m. That's going to give me x double prime plus k over m times x equals 0. Now what I'm going to do is I'm going to make a substitution. I'm going to call k over m is equal to omega squared. And the reason that I'm going to do that is because then this is going to give me nice solutions. You're not going to do it this way when you actually solve. You're just going to plug in your m and your k and you're going to solve it the way you normally would. Okay. But to look at the general form of it, we want to make it look pretty. That's all I'm doing here. So this just means that you're going to end up with x double prime plus omega squared x equals 0. Now, if we're solving this, omega squared is a constant, right? It's a number, whatever your spring constant is divided by your mass. So you're going to solve this using your characteristic equation, which is n squared plus omega squared equals 0. Okay. Move your omega squared to the other side. Take the square root. That's going to give you n equals plus or minus the square root of negative omega squared, which is plus or minus omega I. That's why I made it something squared, right? Because we're taking the square root. When we get something with i's, our answer is sines and cosines. So what we get here is that y equals c1, the sine. This isn't y, it's x, because it's position. So x of t is equal to c1 sine omega t plus cosine, c2 cosine omega t. So that is what the general form looks like. Now, typically, for my physics people, your mass spring systems, the motion of your mass springs is given as what? So in physics, if you were to be doing a physics lab on a mass spring, on a spring, like in what, like intro to physics, right? What does the solution look like? Is it sines and cosines? It's just sines. So that's what we're going to do next. How can we show that this is the same as something that looks like this, right? You're used to this one where there's an amplitude of your sine wave. And then you have omega t, which dictates your period. And then phi here is your phase shift. Right? So typically we have it looking like that. Now, why is that the same here? And how can we coordinate our C1 and C2 to the A, omega, and the phi over here? Okay. Well, we already know what omega is, right? Omega is that K over M. All right. And we know that our phase shift is going to end up being 0, right? Because we didn't have sine and cosine plus something. Okay. So how do we convert this between the two? Right? So here's what you're going to do. You want to show that A sine of omega t plus phi is equal to C1 sine omega t plus C2 cosine omega t. How in the world are we going to do that? Any ideas? I'll give you a hint. We take this side and expand it, right? Using this identity, right? Then the A here is the omega t and the B is the phi. So here's how we do that. So this is going to be A times the sine omega t times the cosine of phi plus A times the sine of phi cosine omega t. And that's got to be equal to C1 sine omega t plus C2 cosine omega t. So just applying the left-hand side to that identity, where your A is the omega t and your B is the phi. From here, we're gonna just match it up the way we were doing where we were equating coefficients. So over here, I have a cosine omega t, and over here, I have a cosine omega t. So that means their coefficients have to be the same. So this A sine phi has to be C2. And here I have sine omega t, and its coefficients have to match as well. So this C1 has to be A times the cosine of phi. They have to match up. So what we end up with is this. So we have C1 is equal to A cosine of phi, and C2 is A sine phi. And now I'm trying to solve a system of what's equated, essentially a system of two equations and two unknowns, right? Now, if I were given A and phi, I could easily use this set of equations to find your C1 and C2, right? Problem is that we're really going the opposite way, because you're going to be able to find C1 and C2 using your initial conditions that we're going to provide. And I'm going to then ask you, oh, what's the amplitude in the phase shift? So your objective is, given C1 and C2, how do you find A and phi? Well, what we're going to do is we've got to get rid of, in order to find A, you've got to get rid of your sines and your cosines, right? So that means we're going to add them up and square them, because I have an identity for sine squared plus cosine squared equals 1. So if you take C1 squared plus C2 squared, what you get is A squared cosine squared phi plus A squared sine squared phi. Wait, do you guys have this page? Okay. Now factor out that A squared on the right. And you have cosine squared plus sine squared, which you know is 1. And so what that tells us is that C1 squared plus C2 squared is A squared. So take the square root. So A is equal to the square root of C1 squared plus C2 squared. Really like the magnitude of the vector, essentially. Right, so that's how we find A. So your amplitude is given by the square root of C1 squared plus C2 squared. To find our phase shift, the phi, you've got to get rid of that A. And since they both have an A, I'm going to divide them out, because if I divide them one over the other, then the A's will cancel out. So if we take, and I'm going to go C2 over C1. So if you take C2 over C1, that is A sine phi divided by A cosine phi. And then your A's will cancel out, and your sine over cosine will become tangent. And that tells you that your phase shift phi is the arctan of C2 over C1. And I'm going to put a little asterisk here, because the only thing we have to be careful of here is that your C2 and your C1 get divided into the proper ratio. So C2 is the coefficient to, all the way back up here, your C2 is the coefficient to cosine, and the C1 is the coefficient to sine. So if you flip them over, you're going to get a different answer for your phase shift. Yeah, sure.
Does it matter what value of data it's
Yeah, I know what you mean. We shouldn't, because you're operating where tangent has a restricted domain. So when you work with the function arctangent, it should be fine. But in theory, they should be equal, right? Like if you're shifting it this direction one, usually it's a plus and a minus or something, right? So if you shift it this direction or this direction, they're going to be within 180 of each other. So it's just going to give you, it's going to like shift it a whole period if you use one or the other. So it's not going to matter. Okay. Typically, like what we're looking for is the amplitude more often than the phase shift. The phase shift is nice for graphing purposes, but typically when you're talking about mass springs, you want to see how high, what your amplitude is, right? How high and low is your mass going to go is the more important question. Okay. All right, so let's look at one where we're going to put all this together. Okay, so what is an example going to look like? So let's go to number 3. Okay, now the number one tricky spot that you have to watch out for here is the difference between whether they're giving you mass or weight. Okay, because they love to change these in the book from mass to weight. Don't ask me why, but that's their thing. So make sure that you're determining whether it's the mass or it's the weight. In this case, your mass weighs 2 pounds. Okay, so your 2 pounds is the weight. And the way you find mass from that is your weight is equal to mg. So you set your mg is equal to 2. Now we're in inches, feet, and pounds, which means that you are in standard units, not metric. So your G here is going to be 32. So in order to find your mass, you're going to take 2 over G, which is 2 over 32, which is 1 over 16. What's the unit of mass in standard units? Slugs, yeah. So it's a 16th of a slug. So that's the first thing that we need. Because in order to plug into my equation, I need the mass and I need the spring constant K. So that one gives us our mass. It tells us it stretches the spring 6 inches. The 6 inches is which variable? That's your S. Now I've got to be careful here because if we're in standard units, then my measurement for distance in standard uses isn't inches. It should be feet, right? So we've got to convert that to feet. So we're going for half a foot is what your S should be. So watch out for your units and watch out for the weighing situation. Now, in order to get K, we're taking mg divided by S. Mg is your weight, which you know is 2, divided by your S, which is the 0.5 or the 1/2. That tells me that your K is going to be 4. Those two things we're going to take and put into our differential equation. So our differential equation is always the same. It's always mx double prime plus kx equals 0, as long as it doesn't tell me anything about a damping force, right? That means it's free and undamped motion. That's the undamped part. Free means it's not attached to anything that's driving that spring back and forth, right? Nothing's moving it after you pull and release, right? It's all on its own. So I'm going to plug in my M and my K into that. Now, the other piece that we need are your initial conditions. So in order to solve this, you need, this is a second order equation, so you need 2 initial conditions. So you need to know what is the initial position? And what is the initial velocity? Okay, so at t equals 0, the mass is released from a point 8 inches below the equilibrium position. Remember, we chose down as positive. So below is going to be +8, except that 8 is in inches and we got to go to feet. So you're taking 8 over 12. Or what is that, 2/3? So that's your initial position. With an upward velocity of 4/3 feet per second. So upward is going to be negative 4/3 feet per second. So this is 2/3 of a foot. And these are the pieces that we put together. So we've got our initial condition. Now we plug in our m and our k. So m is 1/16 x double prime plus 4x equals 0. And then these are our two initial conditions there on the right. So once it's all in here, this is just a problem from section 4.2. So first thing I'm going to do is clear out the 16. If you multiply everything by 16, you get x double prime plus 64x equals 0. And now this is our problem straight from, actually this is section 4.3, because we know we're going to get imaginary solutions, right? So this is going to give you n squared plus 64 equals 0. Subtract your 64. Take your square root. That's going to give you plus or minus 8i. We know that's going to give us x of t equals c1 sine of 8t plus c2 cosine of 8t. And again, to match your c2 over c1, I try to always put the sign first, so that everything's in the right order. So now we've solved the differential equation. Now we're going to use those two conditions. Yeah, Andrew, go ahead. You can. So in this case, your omega squared turns out to be this one, right? And then your omega is 8. It's just a matter of, it's the difference from just solving something that we've solved the same way multiple times before versus trying to learn a new format. So that's why I don't do it that way. I show you the omega squared just so that you can see the format when we do it in general. But we don't really use it in practice, if that makes sense. It's there. We just don't isolate it usually. All right, so from here, we're going to find our C1 and our C2. In order to do that, you're going to use those two conditions. So we know that when we plug in 0, you've got to get 2/3. So 2/3 is equal to, when you plug your 0 in for sine, that one goes away, right? And then we get C2, when you plug in 0 for cosine, that turns out to be 1. So C2 is just 2/3. Because of this, you get C1 sine of 0 plus C2 cosine of 0. But sine of 0 is 0 and cosine of 0 is 1. So this turns out to just be 2/3 equals C2. It's the nice part about using initial conditions when your t is 0. Okay. Plug that back in. Now we've got x of t equals C1 sine of 8t plus 2/3 cosine of 8t. Now we want to use that second condition, but the second condition is on the derivative. So let's take the derivative first. So x prime of t is going to give me 8c1 sine of cosine of 8t minus 16/3 sine of 8t. Now you're going to plug in that second condition. So our second condition says we get negative 4/3 when we plug in 0. So 8C1 cosine of 0 minus 16/3 sine of 0. And again, your sine of 0 is 0, your cosine of 0 is 1. And so we just have negative 4/3 is equal to 8 times C1. Divide both sides by 8. And you get negative 1/6. So that's going to give us an x of t. That is negative 1/6 the sine of 8t plus 2/3 the cosine of 8t. Now, if we want to find our amplitude, and I'm out of time here, but if we're going to find our amplitude, your amplitude is equal to the square root of C1 squared plus C2 squared. So you're going to just plug in your, that's your negative 1/6 and your 2/3. So that's the square root of 1/6 squared plus 2/3 squared. Whatever that turns out to be is your amplitude. And then we know that the phase shift is the arctan of C2 over C1. So that's 2/3 divided by negative 1/6. And whatever those two turn out to be is what your A and your phase shift is. So all of that is only when there's no driving force. There's nothing besides gravity moving your mass after you pull it from equilibrium. And when you're in a vacuum, right? So there's no resistance. So where we're headed next, tomorrow we'll come in and we'll say, okay, what happens if I allow air resistance or water resistance or whatever fluid my mass spring might be in? Okay. We'll work from there. So at the moment we've got homework coming in tomorrow, right? And homework coming in on Friday. And we'll continue working mass springs tomorrow and Wednesday. It's going to be our last topic. So we're done mass springs. We are done. There usually is. Nice. Yeah, if you have the first page in the second set, you want to put them together, grab this table. And I will try to take a look and grade everything.